For as long as we've looked to the stars, we've tried to make sense of it all, to find the rules that govern the cosmos. We've had solid theories for how solar systems are born, where planets can form, and, just as importantly, where they can't. Our own celestial backyard, the Alpha Centauri system just 4 light-years away, was a place we thought we understood. We figured it was too chaotic, too gravitationally violent, for a world like the one we've just found to even exist. So, what if one of our closest stellar neighbors has been hiding a secret that doesn't just bend our rules of planet formation, but threatens to shatter them entirely? Using the most powerful telescope ever built, astronomers have found strong, compelling evidence for a giant planet, a world the size of Saturn, hiding in plain sight. But here's the kicker. It's orbiting a star in a place our best science said was deeply improbable. This is the story of a world that shouldn't exist, a discovery that could be the nearest giant exoplanet we ever find, and a scientific detective story that is only just beginning. To get why this discovery is so huge, we first have to take a trip. 4 light-years away, a stone's throw in cosmic terms, is the Alpha Centauri system. If you're in the southern hemisphere, you can see it as a single brilliant point of light, the third brightest star in our night sky. But through a telescope, that single star splits into a breathtaking spectacle, a dynamic, living system of not 1, but 3 suns. The heart of the system is the binary pair, Alpha Centauri A and B. Alpha Centauri A, also known as Rigil Kentaurus, is the star of our story. It's basically the Sun's twin. A G2 V-class star. It's just a little larger and brighter than our own Sun, with that same familiar, pale yellow glow. Its companion, Alpha Centauri B, or Ptolemy, is a bit smaller and cooler, an orange dwarf. These 2 stars are locked in a spectacular gravitational dance, orbiting each other in a celestial waltz that takes nearly 80 years to complete. At their closest, they're about as far apart as our Sun is from Saturn. At their farthest, they drift out to the distance of Neptune. This constant tug-of-war between 2 massive suns creates an environment of immense gravitational complexity. And then there's the third wheel of this family, Proxima Centauri. It's a tiny, faint red dwarf, and it happens to be the single closest star to us. It orbits its 2 bigger siblings from an immense distance, so far out that its own journey around them takes over 500,000 years. For decades, this system has been a prime target in our search for other worlds. It's close enough to be our first realistic destination for future interstellar probes, and its variety of stars offers a perfect laboratory to study how planets might form in different environments. We've even found planets there already. Around the distant red dwarf, Proxima Centauri, we've confirmed Proxima B, an Earth-sized world in the habitable zone, and Proxima D, a tiny planetoid even closer in. But these worlds orbit a star that's a violent firecracker. Proxima Centauri is an active flare star, constantly blasting its planets with radiation, which makes true habitability a tough sell. The real prize, astronomers thought, would be a planet around the stable, sun-like star, Alpha Centauri A. For years we've searched. We've had hints, claims, and candidates that were later retracted. The general thinking was that if we found anything, it would be a small, rocky world that somehow managed to survive the gravitational chaos. But a giant, a world the size of Saturn? Our theories were pretty clear. That was highly unlikely. The story of how a star system is born is one of delicate creation in the middle of cosmic violence. It all starts with a huge, spinning cloud of gas and dust, a protoplanetary disk. Inside this disk, tiny dust grains stick together, growing into pebbles, then boulders, then planetesimals, and finally, over millions of years, into planets. It's a fragile process that needs a relatively stable environment to work. Now, imagine you're trying to build an intricate sandcastle, but the beach has 2 powerful, overlapping tides swirling around you. That's the challenge of making planets in a close binary system like Alpha Centauri A and B. The immense gravity of the companion star, Alpha Centauri B, acts like a giant, cosmic egg beater. As it swings by every few decades, its gravity mercilessly stirs up and rips away at the protoplanetary disk around Alpha Centauri A. For years, sophisticated computer simulations have tried to model this, and the results consistently painted a challenging picture for planet formation. The models showed that the gravitational interference from the companion star would likely fling material out of the system or send it spiraling into the parent star. This chaos makes it incredibly difficult for the slow, patient process of core accretion, the main theory for how giants like Jupiter and Saturn form, to get going. Any growing planetary core would have its orbit constantly messed with, preventing it from gathering enough material to become a gas giant. This led to a powerful scientific expectation. While small rocky planets might form in stable pockets very close to the star, building a massive Saturn-sized gas giant in the inner parts of the Alpha Centauri, a system was considered extremely improbable. The disk just wouldn't be stable enough for long enough to birth such a behemoth. So, astronomers looked, but they weren't expecting to find a giant. The rules of celestial mechanics seemed to forbid it. And then, the James Webb Space Telescope turned its golden eye to our neighbor, and the rules began to break. Enter the hero of our story, the James Webb Space Telescope. A marvel of engineering, orbiting 1,000,000 miles from Earth. Its 18 gold-plated mirrors are designed to see the faint light from the dawn of time. But they're also perfect for another job, taking pictures of planets around other stars. For this hunt, astronomers used an instrument called MIRI, the mid-infrared instrument. And critically, MIRI is equipped with a coronagraph. A coronagraph is a brilliantly simple idea. It's a tiny, precisely engineered mask that slides in front of the telescope's detector to block the overwhelming glare of a bright star. It's like putting your thumb up to block out the sun. Suddenly, you can see the sky around it, things that were completely washed out by the light. This technique, called direct imaging, is what lets astronomers literally take a picture of an exoplanet. But looking at Alpha Centauri came with a unique and massive set of challenges. First, JWST is so sensitive that a bright, nearby star, like Alpha Centauri can easily overwhelm its detectors. The team had to design a totally custom sequence of super short exposures to handle the star's brilliance without blinding the telescope. Second, and even harder, was the problem of the other star. Alpha Centauri B, though farther away in its orbit at the time, is still incredibly bright, and its glow contaminated the whole view, creating a complex mess of scattered light that had to be meticulously removed. It was like trying to spot a firefly next to one searchlight while standing in the haze of another. The observation campaign began in August of 2024. The telescope stared, the coronagraph blocked the light, and data started streaming back to Earth. Then the painstaking work of data analysis began. Scientists had to develop new algorithms to subtract the light from not one, but two stars. They modeled the light from Alpha Centauri A and subtracted it. They modeled the light from Alpha Centauri B and subtracted that. They scrubbed the images of detector artifacts and cosmic ray hits. And after all that digital cleaning, through the noise, something began to emerge. A single, faint point of light. A dot. A potential world, more than 10,000 times fainter than its star. Finding a dot of light next to a star is the beginning of a scientific detective story, not the end. The first question is always, what is it? Is it a real companion, a planet bound by gravity, or is it an imposter? It could be a distant background galaxy that just happens to be lined up perfectly. It could be some faint object in our own solar system. Or it could just be a ghost in the machine, an artifact created by the complex image processing. The team got to work. The dot's brightness and color in the mid-infrared gave them their first tantalizing clues. The light signature was consistent with thermal emission, heat radiating from a warm, massive object. Based on the latest models, they estimated they were looking at a gas giant planet with a mass similar to Saturn. Even more exciting was its location. The dot was seen about 1 to 2 astronomical units from Alpha Centauri A, an astronomical unit, or O, being the distance from the Earth to the Sun. This meant the candidate planet was orbiting right in the middle of the star's habitable zone, the region where temperatures could allow liquid water to exist on a rocky world's surface. The evidence was compelling, but to prove it's a planet, you have to see it move. A background galaxy would stay put. A real planet would show slow, curved motion as it orbits its star. So, the team booked more time on JWST. They waited for months, and then, in February and April of 2025, they pointed the telescope back at Alpha Centauri A. They ran the same complex observations, performed the same meticulous processing, and held their breath, and the planet was gone. The dot had vanished. For most searches, this would be the end of the story. A one-time detection that doesn't show up again is usually dismissed as a data artifact, a false alarm. But this team wasn't ready to give up. They asked a brilliant question. What if the planet wasn't gone, but was just hiding? The candidate was likely on an elliptical orbit, meaning its distance from the star changes. What if its path had carried it closer to the star during those later observations? So close, in fact, that it was now hiding behind the coronagraph's mask, lost in the star's glare. To test this idea, the team did something extraordinary. They ran millions upon millions of computer simulations. They plugged in a virtual Saturn-mass planet and gave it every possible orbit that fit with that single detection from August 2024. Then they watched to see where those millions of virtual planets would be in February and April of 2025. The results were stunning. In about half of all the simulated scenarios, the planet's orbit would have indeed carried it too close to the star for JWST to see it. Paradoxically, the planet's disappearance became the second powerful piece of evidence for its existence. The non-detections weren't just explained by the orbital models, they were predicted by them. This painstaking work, combining a single positive detection with later non-detections and massive computer modeling, formed the basis of 2 scientific papers. These papers have now passed peer review and been accepted for publication in the Astrophysical Journal Letters, one of the top journals in the field. To be clear, the object is still officially a planet candidate. Confirmation is the final, crucial step, but the evidence is incredibly strong, pointing to an impossible world in our own backyard. This whole process, the puzzling observation, the surprising twist, and the creative problem-solving, is a perfect example of how science works at the frontier. It's a detective story written in data and physics. If you love these deep dives into cosmic mysteries and want to stay on top of the discoveries changing how we see the universe, now's a great time to subscribe and hit that notification bell. You won't want to miss the next chapter of this story. If this candidate planet is confirmed, it won't be just another exoplanet added to the catalog. It will send shockwaves through the astronomical community. The implications are staggering, and they fall into 2 main categories: what it means for our theories, and what it means for our search for life. First, this planet would be a major wrench in our neat and tidy models of planet formation in binary systems. The fact that a Saturn-mass gas giant could form and survive in the gravitationally violent environment between Alpha Centauri A and B is a direct challenge to the prevailing wisdom. It means our simulations are missing something important. Maybe planets can form much faster than we thought, through a process called gravitational instability, where a massive clump of gas collapses directly into a planet in just thousands of years, too fast for the companion star to interfere. Or maybe the planet formed way farther out in a stable region, and then migrated inwards. Either scenario would force a major revision of planetary science textbooks. This object would immediately become a Rosetta Stone for exoplanet science. Because it's so close, it would be the nearest giant exoplanet we know of. It would also be one of the closest in planets to its star ever directly imaged, a huge technical achievement. Unlike thousands of other exoplanets that are just shadows passing in front of distant stars, this would be a world we could study in exquisite detail. We could analyze the light from its atmosphere to find out what it's made of, study its cloud structures, and maybe even map its weather. It would be our local laboratory for understanding giant planets. But the second, and perhaps more profound, implication is its location. The candidate is orbiting within the habitable zone of a sun-like star. Of course, a gas giant like Saturn has no surface and can't be habitable as we know it. But the giant planets in our own solar system host dozens of moons. This raises an electrifying possibility. Could this Alpha Saturn have its own system of large, rocky moons? Imagine a moon the size of Mars or Earth, orbiting this giant, warmed by a sun-like star, with the giant planet protecting it from some asteroid impacts. Such a world could have all the ingredients for life. It could have an atmosphere, clouds, and oceans of liquid water. And here, data from NASA Chandra X-ray Observatory gives us more hope. It's revealed that the radiation environment around Alpha Centauri A is surprisingly calm, even milder than our own sun's. This is a huge contrast to the violent radiation storms that plague the planets around Proxima Centauri. A calm star is crucial for a planet, or a moon, to hold on to its atmosphere and water over billions of years, giving life a stable chance to begin. The existence of this giant planet in this specific spot suddenly opens up a whole new, incredible place to look for a second Genesis. The discovery of this candidate planet isn't an ending, it's the firing of a starting gun. The next decade of astronomy will be shaped by the quest to confirm this world and figure out what it all means. The most immediate step is confirmation. The science team has done its homework. Their orbital simulations aren't just an explanation for the past, they are a prediction for the future. They have calculated where and when the planet should reappear from behind the coronagraph's mask. New observation time on JWST is already being planned to point it at those precise coordinates at that precise time. It will be a make-or-break moment. If the dot of light reappears exactly where predicted, the planet's existence will be confirmed, and the discovery will go down in history. But JWST is just the beginning. Launching later this decade is NASA Nancy Grace Roman Space Telescope. While its 2027 launch date might slip, its promise remains. Roman is equipped with a technology demonstrating coronagraph instrument designed to push direct imaging to incredible new levels. Crucially, Roman sees invisible light, while JWST sees in infrared. By combining data from both, we can learn even more. JWST data tells us the planet's temperature, which helps estimate its mass. Roman's data will tell us how much starlight it reflects, which reveals its size and cloud cover. Together, they'll paint a far more complete picture. Looking further ahead, a new generation of behemoths is rising on Earth. The extremely large telescopes, or ELT, 30 to 40 meter class telescopes in Chile and Hawaii, will have light collecting power that dwarfs anything we have today. With their advanced optics, they are poised to not only study this gas giant in stunning detail, but they could have the power to hunt for even smaller, Earth-sized planets in the Alpha Centauri system. And this brings us to the ultimate dream. Finding a complex planetary system right next door makes Alpha Centauri an even more irresistible target for our first true interstellar mission. An ambitious concept called Breakthrough Starshot is already working on the foundational tech for this grand endeavor. The idea is straight out of science fiction but based on real physics. Fleets of tiny, gram-scale star chips attached to sails just meters across. A powerful ground-based laser array would push these sails to an astonishing 20% of the speed of light. At that speed, the journey to Alpha Centauri would take just over 20 years. These tiny probes could fly through the system, snapping pictures of Proxima b, swinging by this new Saturn and its potential moons, and beaming back the first close-up images of another solar system. It remains a long-term aspiration, but this discovery transforms it from a vague dream into a focused goal. We started with a story about rules, the cosmic laws that told us where a giant planet couldn't be. We followed a trail of clues from the most powerful telescope ever built, which gave us a glimpse of something that defied expectations. We saw how dedicated scientists, faced with a disappearing planet, used computational brilliance to turn a mystery into powerful evidence. And now, we stand on the edge of a potential paradigm shift in our understanding of the universe. If confirmed, this Saturn-sized world in the habitable zone of Alpha Centauri A is more than just a planet. It's a laboratory for understanding how planets form in the craziest environments. It's a signpost pointing to a new place to look for habitable worlds, not on the planet itself, but on its potential moons. And it's a tangible target, a world right next door that future telescopes, and maybe even future spacecraft, could one day visit. For hundreds of thousands of years, humanity has looked up at Alpha Centauri and seen a familiar, distant star. Now, we see a puzzle box, a system of immense complexity and shocking surprises. We thought we knew the story of our own cosmic backyard, but it turns out the most exciting chapter was just waiting to be read. What do you think is waiting for us on a potential moon orbiting this newfound giant? A water world, an ice world, or something we can't even imagine? Let me know your thoughts in the comments below. And as always, thanks for venturing into the cosmos with us.